In this video, I want to prove this formula. A implies B implies C implies A and B implies C. And I want to prove this twice, once using lambda terms directly and once using tactics in Lean. For the proof using lambda terms directly, we start by placing an underscore. Start a new line. And this underscore should turn eventually into a proof that, as I typed before, A implies B implies C implies A implies B implies C. The main connective in this formula is an implication. So we start by assuming H. And then we see that a hypothesis has been put into the context. A implies B implies C. And we still have to prove A and B implies C. The main connective in this formula is again this implication here. So there are implicit parentheses around A and B. So we continue by assuming K, where K is a proof of A and B, and it remains to prove C. Now, H is a formula, is a proof H is a proof that allows us to derive C from something else. So what we do is we reason again backwards. We want to arrive in C, and H ends up in C, so that's perfect. So we use H, and H takes two arguments. So we place two underscores after H. The first underscore here, this underscore, is we need to fill it with a proof of A. And the second underscore we need to fill with a proof of B. So often these proofs will be very long, and then it is convenient to place parentheses right away around these underscores so that we don't get confused. Here, on the other hand, the proof of A will be very short. We can extract it from K, namely the first component of K is exactly a proof of A. So we can use K.1 as the proof of A. And the second component of K is a proof of B. So we can just use that one. K.2. This concludes the proof using lambda terms of this long formula. Now we are going to prove the same proposition again using tactics. Tactics are enclosed in the keyword between the keywords begin and end. And placing our cursor between the two lines, begin and end, we are being shown the goal again. The proof using lambda terms started by assuming something, and this in tactic mode is done with the keyword intro. So we do the same. The tactic proof will mirror the proof using lambda terms, and the assume, what is called assume here, in tactic mode will be done with the keyword intro for introduction. Intro gives us this hypothesis in the context, and it remains to prove this implication. A and B implies C. So again, we have an implication in the goal. We use the introduction tactic to put the antecedent of the implication into the context. So we get a hypothesis K that is a proof of A and B, and it remains to prove C. H, now to prove C, we use H because H allows us to produce something in C, given some other inputs. So we are going to use or to apply H in order to construct a proof of C. And this is simply done with the keyword apply. And when we apply H, we see that two subgoals are created. One is to prove H, and one is to prove A, and one is to prove B. And these A and B correspond to these two inputs here of H that H needs in order to produce an element or a proof of C. So this A here corresponds to this A here, and this B here corresponds to this B here. So when we have two subgoals, then we enclose them into braces, or we enclose the proofs of these two subgoals into braces to not be confused and to not get mixed up between the two different subgoals. We are now only shown the first subgoal since we have placed our cursor into the first pair of braces. So the first subgoal is to prove A, and to prove A we will use K here, and our proof will be exactly the first component of K. So what we will do, we will apply K.1, and that will solve the first subgoal. So we are shown here that the message that no goals are left. That's only true in the sense that within the first subgoal, we have no goals left. When we place our cursor into the second pair of braces, we see the second subgoal that we still have to prove, which is we have to prove B, having again at our disposal hypothesis K, H and K. And in order to prove B, we will again use K, but this time we will use the second component of K. And then with this proof, we are also, with this tactic apply K.2, we are also solving the second subgoal. This concludes our two proofs of this formula that is part of what is called currying in or uncurrying in functional programming, which is to transform a function that takes two arguments into a function, a function that takes a pair of arguments into a function that takes two arguments, and vice versa.